In this video, we'll explore operational amplifiers, op-amps, and see how they work in two classic circuits, the inverting amplifier and the non-inverting amplifier. Step by step, we'll learn how to calculate the gain for both, and as a real-world demo, we'll build a sound-reactive LED circuit that changes brightness with volume, powered by an op-amp. So stick around till the end to see these amazing amplifier circuits in action. 1, 2, 3, go.
First things first, what exactly is an amplifier? At its core, it's just a circuit that takes a tiny, weak electrical signal and makes it bigger. Most signals in electronics start out really small. They need a boost before they can be processed, passed to the next stage, or used to drive a device. Take a microphone and a speaker, for example. The mic converts your voice into an electrical signal, but that signal is far too weak to power a speaker on its own. That's where an amplifier comes in. It strengthens the signal so it becomes usable.
The amplifier's main job is to increase voltage, but without changing the shape of the original signal. And while amplifier might sound intimidating, the idea is actually pretty simple. Even a single transistor can be wired up as a basic amplifier. But when engineers want something precise, stable, and easy to use, they usually grab an op-amp, an integrated circuit built from dozens of transistors and components all working together inside a tiny chip. If you're brand new to op-amps, I recommend checking out our introduction video first. The link's in the description.
Here's a component-level diagram of a typical operational amplifier. It looks complicated, but don't worry, we almost never use this full schematic in practice. Instead, we represent an op-amp with a simple triangle symbol. It's clear, universal, and much easier to work with. The op-amp has two inputs and one output. The non-inverting input is marked with a plus sign and the inverting input with a minus sign. We'll see exactly how they behave in a moment. Op-amps are packaged as integrated circuits, or ICs, which makes them super convenient. All those transistors and components are already built in. You just drop the chip into your circuit and add a few external parts. Since most projects need more than one, op-amps are usually sold in pairs or quads. One of the most common is the 8-pin dual op-amp package, which has become a standard in electronics. And the best part? They're incredibly cheap. You can pick up dozens for less than the price of a coffee. To power an op-amp, we usually use a dual-rail DC supply. That means one rail provides a positive voltage, say anywhere from +5 to +15 volts, and the other provides a negative voltage, like -5 to -15 volts. With both rails connected, the op-amp's output can swing above and below 0 volts, which is perfect for handling signals that go positive and negative, like AC waveforms. But many modern op-amp chips are designed to work on single-rail supplies too. In that case, you only need a regular positive voltage source, just like the ones used in most everyday circuits. There are a few key things to keep in mind when working with op-amps. First, they don't draw current from their inputs, which means they won't disturb delicate sensors or circuits they're connected to. Technically, there is a tiny leakage current, but it's so small we can usually ignore it. On the output side, an op-amp can both supply and absorb current, and thanks to its low output impedance, it can drive loads with very little voltage loss. And now for the most important feature of all, gain. An op-amp gets its name because it amplifies, and what it amplifies is the voltage difference between its two inputs. If the inputs are V1 and V2, the op-amp multiplies their difference, V2 minus V1, to create the output. This idea of gain is central to everything an op-amp does, and the actual gain you get depends entirely on how the op-amp is wired into the circuit. Op-amps are usually used in one of two ways, open loop or closed loop. In open loop mode, there's no feedback from the output back to the input. The gain here is enormous, anywhere from 100,000 to over 1 million. That's why open loop is mainly used in voltage comparators, where the only job is to detect which input is higher. For more on that, check out our comparator video. The link's in the description. Most of the time, though, we use op-amps in closed loop mode with negative feedback. That means part of the output is fed back to one of the inputs, usually through a resistor network. Negative feedback tames that huge gain, keeps the circuit stable, and makes the op-amp behave in a predictable, linear way. Closed-loop op-amp circuits are everywhere, from inverting and non-inverting amplifiers to summing amps, difference amps, integrators, and differentiators.
In this video, we're focusing on two closed-loop configurations, the inverting amplifier and the non-inverting amplifier. To analyze them, we use two simple but powerful rules, often called the golden rules of op-amps. They come from the ideal behavior of an op-amp, and they make circuit analysis much easier. Golden Rule 1. No current flows into the input terminals. That's because an ideal op-amp has infinite input impedance. Golden Rule 2. With negative feedback, the voltages at the inverting and non-inverting inputs are equal. The op-amp constantly adjusts its output to make the difference between those inputs as close to zero as possible. These golden rules only apply when negative feedback is present, but when it is, they give us a really simple way to predict how the circuit will behave.
With those rules in mind, let's look at two of the most important op-amp circuits, the non-inverting amplifier and the inverting amplifier. We'll analyze both of these step by step, using the golden rules as our guide. First up, the inverting amplifier. Here's how we build it. The output is fed back into the inverting input through a resistor, RF, and another resistor, R1, is connected to that same inverting input. The input signal passes through R1 into the inverting input. Then, RF links the output back to that input, forming the closed loop. In this configuration, the non-inverting input is used as a reference point, so we connect it to ground. That way, the input signal flows through R1 into the inverting input, and we get our output at the other side. Now let's analyze the inverting amplifier using the golden rules. Let's call the voltages at the inputs V1 and V2, and the currents through the resistors I1 and I2. Golden Rule 1, no current flows into the op-amp inputs. That means the current through R1 is the same as the current through RF. Golden Rule 2, with negative feedback, the op-amp keeps the inverting input at the same voltage as the non-inverting input. Since the non-inverting input is grounded, the inverting input is held at what we call virtual ground, essentially 0 volts. These two relationships make the math pretty simple. The current through R1 is equal to the current through RF. And by Ohm's law, current is just voltage divided by resistance. The voltage across R1 is Vin minus V1, and the voltage across RF is V1 minus Vout. But from the second golden rule, we know V1 equals 0, since the inverting input is at virtual ground. That simplifies things nicely. Vout equals Vin multiplied by negative RF over R1. From this, we can calculate the gain of the inverting amplifier. The gain is negative RF over R1. This also means we can adjust R1 and RF to set the gain to whatever we need. Pretty neat, right? Now, the negative sign is really important. If the input is a sine wave, the output is still a sine wave, but flipped upside down and scaled by the gain. In other words, the output is inverted compared to the input. You can see this clearly on a voltage versus time graph. And this inversion isn't a drawback, it's actually very useful. Later in the video, I'll show you a sound-reactive LED circuit that uses this exact inverting amplifier setup to make LEDs glow brighter as the volume goes up. Next, let's analyze the non-inverting amplifier. Here's how we build it. Just like before, the output is fed back into the inverting input through a resistor RF, and another resistor R1 is connected from the inverting input down to ground. The input signal, however, goes directly into the non-inverting input. In this setup, the inverting input isn't grounded directly. It acts as a reference point controlled by the feedback network. With that in place, the op-amp balances itself so the output responds to the input properly. Now let's go through it using the golden rules. Let's call the voltages at the inputs V1 and V2, and the currents through the resistors I1 and I2. Golden Rule 1, no current flows into the op-amp inputs.
That means the current through R1 is the same as the current through RF. Golden rule 2, with negative feedback, the op-amp keeps the inverting input at the same voltage as the non-inverting input. Since the non-inverting input is where we applied Vin, the inverting input is also held at Vin. That makes the math pretty straightforward. The current through R1 equals the current through RF. And using Ohm's law, current is voltage divided by resistance. The voltage across R1 is 0 minus V1, and the voltage across RF is V1 minus Vout. But from Golden Rule 2, we know V1 equals Vin. Rearranging gives us Vout equals Vin multiplied by 1 plus RF over R1. So the gain of a non-inverting amplifier is 1 plus RF over R1. And just like before, we can adjust R1 and RF to set the gain to whatever we need. Pretty neat, right? And here's the key difference. If we plot the input and output, they're in the same phase. The output is amplified, but not flipped. That's why it's called a non-inverting amplifier.
Both inverting and non-inverting amplifiers are really useful. You just need to remember their different circuit setups and how the output behaves when you use them in a project. To make this crystal clear, let's look at a simple, real-world example, a sound-reactive LED lamp. In this circuit, the LEDs change their brightness in step with the sound. Twinkle, twinkle, little star, how I wonder what you are. Up above the world so high, like a diamond in the sky. Twinkle, twinkle, little star, how I wonder what you are. In this lesson, I'll focus only on the amplifier part. If you'd like the full breakdown of every component, I've made another video that covers it in detail. The link's in the description. Our input comes from a small condenser microphone. After passing through a coupling capacitor, the mic gives us a tiny signal. If we measure it, the peaks are only about 165 millivolts. That's just a little wiggle of voltage, nowhere near enough to light up LEDs. Here's what the LEDs actually need: about 4.5 volts to glow faintly, around 6.15 volts for full brightness, and if the voltage drops below 2.85 volts, they switch off completely. Now, compare that with the microphone's output. The mic signal only swings by about 0.33 volts peak to peak, but to control the LEDs properly, we need the output to swing by about 3.3 volts peak to peak. That's almost 10 times bigger. So we need an amplifier with a gain of 10 to stretch that tiny mic signal up to LED driving size. We could build this using either an inverting or a non-inverting amplifier, but let's go with the inverting setup for now. To get a gain of 10, we just need the right resistor values. If we pick 1 megaohm for the feedback resistor, RF, and 100 kiloohms for R1, the math works out perfectly. Gain equals 10. And don't worry about the negative sign in the formula. The LED wiring takes care of the inversion for us. With this setup, the circuit takes the microphone's tiny signal and makes the LED brightness dance in sync with sound. For this demo, I used an LM358 dual op-amp, but really almost any general-purpose op-amp will do the job. And that's it for this build. If you'd like the full step-by-step explanation, check the link in the description. If it's not there yet, hang tight, I'll be uploading it soon. Op-amps open the door to so many amazing projects, and I'll be covering plenty more in future videos. In this episode, we explored two of the most basic but important op-amp circuits, the inverting and non-inverting amplifiers. If you'd like to support the channel, you can do so on Patreon. And if you have any questions, drop them in the comments. Your feedback really keeps us going. Thanks for watching, and don't forget to like and subscribe for more fun educational videos.